Okay. Let's see. I guess people can hear me. Okay. A couple things. First, just while I'm still fussing around with the projector, I noticed that you go to the university homepage today. The lead news is Stony Brook University senior awarded prestigious Churchill Scholarship. Okay. And the important thing about this student is that he took the algorithms class. I think it was last year, if not the year before. And so may you all go on and win Churchill scholarships and be like him. Any questions about the Churchill Scholarship? Yes?
The guy is the president of Math Club and schools use.
Okay, but most importantly, he took the algorithms class. That's the important property here. Okay, let's try to get this set up here. I'm almost, think I figured some of this stuff out. Boom. Okay, so let's start off first of all. Are there any questions about anything technical or logistical? I passed out the homework one. People should be getting going on it. Some people may still be looking for partners. Who is still looking for a partner? I see one. I see two. I see several. If you are looking for a partner, stand up. If you are not looking for a partner, sit down. Okay? Now make eye contact at people. Look around, try to find somebody, okay, and then make signatures, right? Okay? Just look at you people like this kind of thing, okay? If you're telling me, no, this is too random and too arbitrary, instead you can email me, and I will randomly assign you to the next person who emails me, okay? I've done that with a couple people, whatever you feel more comfortable with, okay? But pair yourselves up and get working on it. Any questions about that? Okay. Any other technical questions? Yes. You need a partner. I strongly encourage a partner. And let me explain why, because people don't always understand this, okay? There are several ways of getting yourself in trouble in this class. One of them is to find out that a lot of the problems have answers on the web if you look for them. Why is that trouble? It's not that I'm going to take off any points for it. It's not that I'm going to stop you from, that we're going to accuse you of cheating or anything like that. But what I can guarantee you is that the way you learn these things is by beating your head on it and arguing with someone about it. And you can't argue with an answer that is on the web. Is that clear? Okay. So I think that the right way to do it is, with these problems, a light has to go on. Okay, and the right light has to go on, okay? And I find that this is best done by working with partners, okay? So do you absolutely have to work with partners? The answer is no. Do I think it is a good idea? The answer is yes, okay? And I do strongly encourage it. If you find that you can't get along with your partner and you want to break up and find a different partner next assignment, that's good, okay? But I encourage you to beat your heads against these problems instead of just trying to see where you can find an answer, because that's not going to help you, okay? And I encourage you to sort of do it by arguing with someone. That someone might be a TA, that one someone might even be me, okay? But I encourage you to be your partner. Yes?
Would you like us to collect actual data from the school library or just estimation?
Okay, so these estimation problems, some people have gotten are wanting to know about the estimation problems. Okay, so an estimation, first of all, why do people take algorithms classes? There are good reasons and there are less good reasons. One of the less good reasons is that on every job interview you go on, they're going to ask you algorithm questions. And that's because it's about something about there's a learning a way to think about things. And one class of problems that's useful to go away and think about things is to learn how to estimate. I mean, in some sense, what is the big O about? It's about an approximate, rough way to think about how long a program is going to run, right? That's what you're learning with the big O, is you're coming up with a way of estimating how long will this program take to run if I coded it up and if I ran it on a real computer, right? So for that reason, the estimation problems I give, I think, are good for warming up yourself up for how you think in this kind of a manner. Should you go to the library and count how many pages there are to figure out how many pages there are in the library? The answer is no, okay? But can you estimate how many books are there in the library? Yeah. And my guess is that there is a principled way to do it, okay? you can, by just a little bit of reasoning, you should be able to get within an order of magnitude, and that is good enough. Learning how to do these kind of back-of-the-envelope calculations is a valuable thing, and that is why I have them on here. Okay? Any questions about it? Am I going to argue with you too wildly if you're off by a different order of magnitude than me? No. Okay? But learning to think about it, and sometimes learning to estimate in two different ways and seeing how close you get the same answer to is sometimes a sensible thing. Okay? But bottom line, that's to train estimation skills, which I think are very important. Any questions? Any? Yes?
Do you want us to hand this in on 9 separate sheets of paper?
I want you to hand it in on 9 separate sheets of paper. Okay? If I have 9 problems there, I want you to do it on 9 sheets of paper. If you're telling me, no, I can really fit these estimation problems, don't have to all go on different papers, maybe set one side of a sheet of paper, don't use more than one side, and don't spill over onto the next sheet of paper. That's the critical thing. Okay? Just to make it not so hard to grade. Any questions? Yes? Can I give you a worst example about what? What should you try to do with the algorithm solution? Again, recognize here the problems are on big O notation things. So it's a little different than the rest of the class where we'll be doing more about algorithm design and things like that. For these, do I have any particular advice? The important thing I would say is make sure, okay, for ones that involve an idea, make sure we know what the idea is. So writing one sentence, my idea is this. So for the case of estimating how many books are in the library, a bad answer is 1 million times 63 times 92. Okay? A better answer is to say, well, I'm going to be doing it by how many books get published in the universe, because you figure that there's a million people in the world, 100 million people in the United States, and 1 out of every 100 of them is an author, and they write 1 book, okay? And that's how many books there are. And the libraries here are crummy enough, they buy 10% of them. Okay, that may be what your reasoning is. So explain what your reasoning is, okay? And that's really what my only advice for now, okay? I guess I'll have stronger advice when it comes time to more algorithmic stuff, but which hopefully we'll start to get into today. Any questions about that or anything else? Okay, I'd like to start with the daily problem. And the daily problem is, again, a big O problem. If I am correct, it is problem 220. And let me see if I have let me try something here. Ka-chunk. Where can I do it? This is not the daily problem, but I think it's got some space. Let's see if I can do this daily problem here. And if not, I'll go to the blackboard. What is the daily problem? The daily problem asked for pairs of functions, and it asked you to decide, it gave you certain pairs of properties that you needed between f and g, okay, certain relations that held there, and then find concrete functions f and g that hold these relationships, or if they don't exist, say so. So what is the problem? It says, like, the first property we're looking at here seems to be we want to know that f of n is little o of g of n. We also know that f of n is not equal to theta of g of n. And I have to give you functions that satisfy those two things. Can everybody see this? Is that acceptable writing? So how would I do this? Okay? My first thing is I would try to translate this into a picture. Okay, so I find these very complicated to deal with. If you draw a picture, I can understand it better. So what is my picture? Here is, when it says here that f of n is little o of g of n, what does that mean? That means that if here is some function g of n, where is f of n? Is it below it? Is it close to it or really below it? It might as well be really below it. Okay, this is little o, right? It means beaten up on, right? So I am picturing here I've got f of n. Right? Does everybody see that? Now, if f of n is not equal to big O of g of n, that means that f of n is not tightly bounded by things, right? Is it possible for this to be some g of n? It's not, saying it's not theta of g of n. If it was theta of g of n, it would be tightly bounded by g of n. Okay? We're saying that's not true. Is this possible? And I think the answer would be yes. Suppose f of g of n was much bigger than f of n. F of n is not theta of g of n, and this would hold. So what would be examples of functions that might work? Yeah? So you would be saying that g of n is equal to something like n squared, okay, and f of n is equal to n, and that satisfies that as far as I am concerned. Any questions about that? Why that is? Any functions where there is a dominance difference here would work. You want to make this log n, you can do it. Okay? You want to make this log n squared and this log n, that's fine. Okay? Any questions about that? That I think is now pretty clear. Let's look at the second one. Let's see now if we can erase it and try to do the same thing. Ka-chunk, ka-chunk. The next one says what? We know that f of n is theta of g of n. Let's write these things down. F of n is equal to theta of g of n. Okay? And we're saying that f of n is little o of g of n. Right? Is that possible? Well, I don't know. It's complicated. I got to draw a picture. What is my picture going to tell me? First here, if I'm drawing my function f of n, where must g of n be? Okay? If I've got this theta relationship, okay, what does that mean? That sitting right above it is some constant 1 times g of n, right? And sitting right below it there is some constant c2 times g of n, right? Nestling f of n snugly around it, right? Is that what it says? What is the second statement? It says that f of n is little o of g of n. For this to be true, what is the situation? That f of n has to be way down here, right? So to satisfy this, f of n has to be way below g of n instead of snuggled by it, right? So my claim is this is a contradiction. It can't simultaneously be both of these things. How many people agree with me? How many people don't agree with me or have questions? Okay, so I see a contradiction here, and I would write none. Any questions about that? Okay. How do I do the third one? Oops, not that way. Okay, how do I make that go away, or do I have to end the lecture? No. Let's now try no. Let's try clear. Katunk. How do I make this bigger? Like that? Right. Get bigger, right? No. View. I have had students who say that they've enjoyed watching me fuss with the projector all semester. But, okay, what's the next third one? The third one says, if I'm going to write it down, it says that f of n and g of n, f of n is theta of g of n. And we also know that f of n is not equal to big O of g of n. Is that right? Okay. Could that be done? Well, let me draw a picture. What does that picture mean? If here I've got f of n, where is g of n? There is a constant times this, okay? And times g of n, and there's another constant, c2, times g of n below it. Now you're telling me that f of n is not big O of g of n. And I have to say, wait a second. I've got this function here, right? What is this thing? I've got that there is a constant times g of n that is bigger than f of n. From up here, this says I can't have it. That is a contradiction. And so the answer here is none, right? Can't do it. Any questions? Okay. Finally, what's the other one? If I look at this thing, it's telling me that, if I write it out, f of n is equal to omega of g of n. And it's also telling me that f of n is not equal to O of g of n. So what does that mean? If f of n is omega of g of n, what does that mean? That means that here is f of n. Where is g of n? Above it or below it? Below it. Here is g of n, right? And now I know what that situation is. Now you're telling me that f of n is not in big O. You're telling me, is it okay that f of n, if it's not in big O, that means that it is not less than or equal to some constant in this. And I don't see any contradiction here, right? If I make this n log n, and I make this n, both of these things are satisfied, right? N log n is not in big O of n, right? But n log n is lower bounded by n. So this is perfectly reasonable. Any questions about that? Okay? Any questions about this stuff or working with the notation? Okay? Whenever I get confused, I draw a picture. I go back to the definition, and these things work themselves out. Any questions? Okay. Fair enough. What I'd like to do now is, last class I talked a little bit about, I started talking about logarithms. I left out one very, very important property of logarithms that I want to make sure we talk about and understand, because there's sort of some magical things going on here. First question is, what does a logarithm mean? What is the log of n in Skinner language? Okay? I would define it as the number of times you have to double, start from 1 and keep doubling till you get to n, right? Or the number of times, if I have n, how many times do I have it to get down to 1? That's in my heart of hearts what a logarithm is. Now, the truth is that is a base 2 logarithm. And logarithms are, the real definition of a logarithm is this, okay? That for any integer c, or any constant c, c raised to the log base c of x is going to give you x, right? The log here is, the log of x is going to be to what power must I raise c to get x? That is what the definition of the logarithm is. Any questions about that? Now, in principle, you can have logs of any base. That much should be clear. What is the base 3 log of 27? What power do I have to raise 3 to make it 27? 3. Does everybody see that? And that's the log base 3 of 27 is 3. Okay? So we can have logs of any base. But in my way of thinking for this semester, I am going to generally ignore the base of the logarithm. Now, why is that? The reason is this formula, which you learned in high school, to convert bases of logs. You took logs in high school. That was a long time ago. Okay? But you had a formula that looked like this, which said that the log base b of a is the log base c of b, log base c of a, divided by the log base c of b. How many people recognize that formula? You may not remember where the a's and the b's and the c's go, but this should look familiar. What is the implication of this? Suppose, let's say, I want to compare something which is a log base 100 with a log base 2. Okay? What is the relationship between log base 2 of n and log base 100 of n? Okay? Rhetorical question still. Okay? What does it mean? Look at this formula. A is here. This is the n roll. This is the n roll. One of these is 2. One of these is 100. Right? B and C are the 2 and the 100. What is the log base 2 of 100? Okay? It should be clear that it is a number. Okay? And it is a number independent of a variable. Okay? It is a number you punch in your calculator and you get a number back. Right? That means that to convert between any one base log and any other base log, where if this was the thing we're taking the log of, to convert between those logarithms, we're just multiplying it by or dividing it by a constant that's a function of these two bases. So converting between a log base 2 and a log base 100 is just multiplying or dividing by something. Does everybody see that? Something being a constant. 6, 2, 1. I don't know what the constant is. Your calculator does. But I know that it's a constant. And what does that mean? That means that the log base n, base b, this is going to be theta of the log base anything else of n. Does everybody see this? Because here I've got a log base c. Here I've got a log base b. Are those functions different in a big O sense? No. Because to convert between the log base c of n, I am simply going to be multiplying it by a constant times log base b of n. Okay? So big O-wise, the base of the log does not matter. How many people understand what I'm saying here? This is a critical point. How many people are confused by this or have a question? Question is a good one. Okay? So in a big O sense, okay, it isn't going to matter. Okay? So if we think about it, suppose we had a tree, not a binary tree, but a ternary tree. Okay? Where instead of branching 2 ways, we branch 3 ways. How tall does it have to be until I get n leaves to it? This is a 3-way array tree, right? On the first level, there are 3 nodes. On the next level, there are 9 nodes, right? What is the height of that tree exactly to get n leaves? Okay. What is it? It is log base 3 of n. Log. No. Okay. Log base 3 of n. Right? Now for my binary tree, it was log base 2 of n. Right? Which of these is bigger? Log base 2 of n or log base 3 of n? Which is bigger? Remember, this is going to be the height of the tree that generated those n leaves. Which is going to be bigger in an absolute sense? Log base 2 is going to be bigger than log, right? You're going to grow a total of n children. You want to have n descendants. Should everybody have 2 babies or should everybody have 3 babies? If you want to get to 1 million descendants, put out 3, right? But in a big O sense, this isn't that different. The difference between log n, base 2 of n and log base 3 of n is either multiplying it by or dividing it by the log base 2 of 3 or 3 of 2, okay, which is a constant. So big O-wise, they are the same thing. Any questions here? So in life, we are going to ignore the base of the log, okay, because we think at this high level, big O sense. Any questions about that? Yes? Okay, you're saying, but wait a second. Isn't there something going on different between the log base? What you're saying that's very interesting is that I believe, Skeena, you believe there is a difference between n to the well, say n cubed and n squared. I believe that, right? But I'm claiming that that the base of the log doesn't matter. What happens if I take the log of both of these things? Okay? This is an interesting point. What is the log of n cubed going to be? Log base 3x of n. So what's that going to be? That's going to be something like the log of something. That's 3, I think, log n. Is that right? With some base here, right? Depends what base I did, right? What's the log of this going to be? 2 times log base b of n. Okay? Once I hit something with a log, are these functions any different? Big O-wise, they are not different if you look at them, right? The meat of the thing is a log base b of n, right? Multiplying by 2 or 3 is a big O difference. There's no big O difference. It's just multiplying it by a constant, right? So the log operation is so powerful, it chops any power down to size, okay? And it's so powerful that the small difference of what the base conversion is not interesting in a big O sense. Any questions about that? Actually, let me just prove one thing very quickly, okay? Or convince you. Proof means I would rather convince you, okay? Where does this kind of equation come in? Okay, where did this thing come from? Okay, again, you saw it in high school, so it must have been true. But let's think about what is happening when we take the height of a tree. Let's say we have a height of a tree that is base 8 rather than one that is base 3. So suppose, let's say we have a tree with 8 children at each level versus a tree that is going to be a binary tree and put out 2 trees per level, right? And this has n children at the end, and this has n children at the end. How much different? This is a degree of 8 out degree. This is a degree of 2 out degree. What is the difference in the height of those trees? Okay. Anybody else? Just to bring someone else? Yes. 3 times. Why is that? Because each one of these steps, in one step it got glump 8 times as many, right? To make this thing 8 times as many, what did I have to do? 3 steps. Does everybody see this? 3 binary steps was the same as 1 base 8 step. And that is why this tree is going to be 3 times taller than that 3, right? And this constant thingy is that 3, okay? That's why all of this is working out the way that it is. Any questions about it? Yes? Are the bases always bigger than 1? Again, what I will say, I think the answer is yes, okay? Let's say, okay, so what's interesting is, in here we're going to talk about bases which are sometimes not integers, okay? So 4/3 is a perfectly reasonable base. Something funny may happen below 1, okay? And so I don't want to, I'm not taking a position right now on logs less than 1, okay? In the context of what we're going to be doing here, we're not going to worry about that. Undoubtedly, the operation's defined and all that, but we're not going to worry about that now. Any questions? But recognize logs do not have to be integers. That is one thing I am going to use somewhere this semester. Any questions? Okay, any questions about logarithms? Okay, because we're going to see them, see how they work in a big O sense, see how the base doesn't really change. Okay, any questions? Okay, let's see if I can get this down. Clear ink. Is this now properly? Okay, wait, no, what did I do here? Bang, edit, view, full size. No, full screen, no. Okay, I think I'm right. Am I right now? No. Okay, let's see what happens. Okay, any questions about logarithms or big O notation? Because now I want to shift gears a little bit to start getting us into the algorithm world. Any questions about big O, math prerequisites, anything I've said? Okay, so what I'd now like to talking about is data structures. And one quote that I always liked was this notion that man's progress is measured by the number of things we can do without thinking. Okay? That there's certain things that you sort of know how to do and you don't have to rethink about it. You don't have to rediscover the idea of how do you multiply numbers, because you can do that without thinking. You learned that in 5th grade, 6th grade, something like that. Okay? Data structures, in my mind, I like to think as something that we have done, and once we have done it, we can do without thinking. Okay? On one level, a data structure is an off-the-shelf component, okay, that we're going to build more complicated algorithms from. It's not quite as, that we're not going to necessarily always use these things completely as a black box. But it's sort of important to know what the basic data structures that are used to represent data and let us do certain operations on them. And to know what their powers are so that we can use them for, designing more sophisticated algorithms. These are going to be things like stacks, queues, heaps, lists, things like that. And you guys have all hopefully taken a CSE 214, the data structures class. That's a prerequisite for the course. Okay? When you take that thing, you're going to learn about data structures. In some sense, it's going to be this notion of data structures and data types. Okay? A data type, okay, is sort of an abstract thing that describes the operations that a data structure has to do, the specifications. The data structure or the implementation of the data structure is how you're actually working with this thing under the hood to implement it. And what we're going to see, starting this class and for the next couple of classes, is that there are certain abstract data types that are very important, particularly we'll talk about a dictionary, okay, where there are a lot of different ways to implement it, which yield different performance on different types of operations. And recognizing that there can be many different ways of implementing the same abstract data type, okay, enables us to pick the one that gives us the best performance for what we need from it, okay? And so thinking about algorithms, thinking about data structures, is thinking about trade-offs. In an abstract data type, there's usually a bunch of different operations you want to be able to do, okay? And there is often a trade-off in being able to do two different kinds of operations. Let's say two operations you would like to be able to do are lift heavy weights and run very fast, right? Lifting heavy weights, the people who are very good at lifting the heavy weight operation, they tend to be big and bulky and slow, right? On the other hand, they beat the crap out of someone who moves slow, who's fast, right? Someone who's fast is often thin and sleek and doesn't carry an extra ounce of anything that isn't going to help move them forward. Recognizing that supporting the operation of lifting heavy weights, okay, requires a different implementation of a person than one that has to run fast, okay? There is a trade-off between two different things. And what we are going to discover in here is that for certain different implementations, realize different trade-offs in how you do different operations. And that's kind of the important principle of data structures. It's a game of playing trade-offs. Any questions about that? Okay, good. So let's go through I want to spend the rest of the class sort of doing, a basic overview of data structures. And I want us to think a little bit about what some of these data structure issues mean, because we're going to use them throughout this semester. The first distinction in data structures that one faces is the difference between contiguous and linked structures. Okay, a contiguous data structure is something like an array. okay, where you allocate one big slab of memory, and you're going to be working in that slab of memory, okay, knowing that it is in one piece. A linked data structure is one where you have smaller pieces of memory, okay, that are sort of logically connected by links, pointers, okay? And certain data structures are built out of memory slabs. Certain data structures are built out of linked structures. What are the good things about arrays and data structures? Let's think about these things. You guys undoubtedly spend a lot of time thinking about arrays and linked lists. What are the good things about arrays? Okay, who thinks arrays are good things? Okay, what is good about an array? You're saying what one good thing about an array is the accessing of a structure. You can access it in constant time. An array, remember, is a slab of memory. You access it by an address. You say, give me what is in this location, the ith position of my slab. The good thing is if I have I can access it in constant time. Okay, that's one good thing about an array. Any other good things about arrays? Okay. Who here likes using arrays better than linked lists? Who here likes using linked lists better than arrays? Some people. Okay. One thing that I think is true, I think of arrays are usually simpler than linked lists. Okay. But what else is good about, okay, anybody else have anything good to say about arrays? Okay, yeah?
They don't take up like extra pointer space.
So one thing that is, if we think about, let's say, what is good about arrays. Clear ink, chunk. Okay? I think that there are several good things about arrays. The most famous, and probably for our purpose, the most important, is that you get constant time access to look something up. The second most important thing, which in a big old world, with our theoretical world, may not be so important, but in practice is very important. Arrays are very memory efficient. Okay? If you use a linked list to store items, you have two fields to store every item, right? There is going to be the data field and the pointer field. In an array thing, where are the indices of an array stored? They aren't stored. They're implicit, right? The index is sort of it's a virtual thing. It's saying, well, if it's I, I'm not storing what I is. I'm just saying that I'm going to know from my starting point and move I spots over to the right, right? So arrays are very good because they don't waste any space, okay? And that's not something to be sneezed at because a linked list, by definition, will, in some sense, waste half your space, okay? In a big O sense, do we care if we waste half of our space? No, half is just a constant, right? If you have to go to your boss and say, buy me a computer with twice as much memory, then that makes a little difference, okay? Any questions? The other issue that's a more subtle thing that I don't want you to get hung up on, but it's worth knowing about in here, is that in real computers, arrays tend to be extra nice things to walk through because of how memory gets cached, okay? Things get cached. And there's often things like prefetch operations, where if you're looking at a particular location in memory, the memory location after it is also brought forth in the cache. So if you walk over to the next element, it's already there and you don't have to load it in from memory. So arrays are often very good things in caches and modern memory. And so we should keep that in mind. So arrays are nice. In a big O sense, does this matter? No. In a big O sense, does this matter? No. Does the index matter? Yes. Constant time access. Okay? But that's why arrays are a good thing. Any questions about arrays? Why are arrays bad things? Does anybody think that arrays are not good things? There's some reason why they are not good. Yes? You might have to reallocate place. Right. Okay. Does everybody see that when you allocate a slab of memory, everything is fine so long as the stuff that you need fits in that slab of memory, right? But if you need more memory, in some sense you have to go and get a bigger slab. And when you get a bigger slab, you've got to copy over the stuff that you had in your small slab, okay, in order for everything to be there, okay? Yes? So you're saying okay, so this is an interesting question. So you're saying here, one bad thing about an array is, what if, let's say, I decided to allocate all the space, I have to allocate space in my array for the maximum amount of stuff that I'm going to be putting in it, right? What happens if, what are the maximum number of people who might go to a Stony Brook basketball game? Well, there are 300 million people in the United States, and maybe they'll all want to go. If I allocate room for all 300 million, if in fact, 65 show up, okay, I have wasted a lot of memory. Does everybody get that idea? Okay? So this speaks to this problem of running out of memory and having to reallocate, or allocating so big and then not using it. Gets to a modern kind of an idea for an array called dynamic arrays, okay? Many of you use programming languages, okay, where there is a notion of a dynamic array, where you don't have to specify how big it is at the beginning. How many people know what I'm talking about? Okay, most people, okay? How is it that dynamic arrays work? Well, what they will do is the following. You will allocate a small amount of memory, maybe an array of size 10 or something like that when you start it off, maybe a size 1 even. Then you happily fill things in, fill things in, fill things in. When you have filled it up, the system is going to say, you want another spot of memory, I need to allocate a slab. I will now allocate a slab that is twice as big, and then copy it over these elements. And now I have half of my array filled and half of my array empty. Right? Does everybody see this? What's good about a scheme like this is I didn't have to allocate 3 million elements in my array. I didn't have to tell you my maximum element size at the beginning. So there is no danger of me suddenly trying to fill my array, declaring an array and not putting a lot of things in it. For me to have 1 million elements in this array allocated for this slab, I have to have had at least 500,000 things already in there, right? Because at this point, only half the space is going to be empty, right? So that solves your problem about leaving it idle, and it solves the problem of knowing in advance how many things do I need, okay? What is the bad thing about this dynamic array? Yes? I've got to copy this element here. Does everybody see this? So if I start out with, let's say I'm going to end up with, let's say 1 million things in my array. Originally, let's say my array size was only 1. I'm going to fill in my array, and oops, now I have to copy. Fill it in, oops, now I have to copy. Fill it in, oops, now I have to copy. Fill it in, okay, then, oops, I've got to copy, right? Then once I have filled this in, then double it again. Does everybody see it? This would have been filled in. Fill in these other elements, okay? How many times, if I end up with n elements in my array, how many elements how many times might an element get copied under this scheme? Okay? Yes. Would it be that an element, how much is one element going to get copied? What's the maximum element that's going to be copied? How many times will it be copied? Yes? Log base 2 of n. Why is it log base 2 of n? Okay, yeah? Okay, doubled. Whenever there is a log, something is doubling, right? So if you think about it, when is element number 1 the first thing it got copied? on what got inserted under what iterations is it going to get copied? Is it going to get copied on the second iteration, on the fourth iteration, on the 8th iteration, on the 16th iteration? That is when things get full and I have to double it, right? So if I'm going to go up to n, how many times do I have to double from 1 to get to n? That is what I mean by log base 2 of n, right? How many people see this? That the most element 1 may have to be copied log base 2 of n times with this scheme. How many people see it? How many people don't see it? Any questions? Good. Okay. So my question now is, what's the total amount of work done in filling up an array of size n? Okay. We now want to start thinking about this in a big O sense. Okay. One of the, let's say, simple and generally very, very useful ideas for analyzing a big O thing is to say, how many operations will I be doing, and what is the maximum cost of any operation? In a big O, what does big O of something mean? It means an upper bound, right? If you want to come up with an upper bound of how much time does it spend to maintain, to fill a dynamic array of length n, a correct way to argue is to say there are going to be at most exactly n insertions. Each insertion can trigger at most log n copying operations, right? That would say an upper bound on the amount of work that you have to do to fill a dynamic array would be n times log n. Does everybody see that? Okay. Filling a dynamic array, you can say it takes big O of n log n because it's n operations, n insertions. Each insertion, each element that I insert might be moved, okay, log n times. Okay? Any questions about that? Do people see why that is a correct thing to say? Okay? Now, the interesting thing about dynamic arrays is, in fact, we're sort of overcounting. Why does this overcount the amount of work that is being done? Okay? Yes, you. Some elements may not have to be copied multiple times. If I look at an array here, at the end, if I have an array that was filled up like this, all n elements filled up, how many times will the elements from n over 2 plus 1 to n, how many times will these elements have been copied? Yeah? Well, they will have been inserted once. How many times would they have been copied into a new array? 0. You know, they're not recopied. They're certainly recopied 0 times. If you want to say how many times was something done with them, they were touched once, right? When they were put in the shelf. So half of these elements were put on the shelf and never moved. Does everybody see that? So that would be one operation for each of these elements instead of log n. That might mean that there is some overcounting going on. When I say that, if I say something takes n operations, each of which is at most log n, that is an overestimate. Yeah?
Can you just have the last element on the dynamic array be a link to another array and do it that way?
Okay, so one thing you might say is another scheme for maintaining these arrays. Let's address this now. You're saying is don't recopy, allocate slabs, and keep a pointer going from each slab to the next pointer. Does everybody see that? And now, how would I access the last element? I would go and say, oops, it's beyond this element. I got to go to that pointer. Beyond that element to that pointer, beyond that element, then here. The total number of elements here was n over 2. n over 2 plus 16 is the element that I want. Okay? Could I do this and do this correctly? Yes. What is the downside of this scheme? The good thing about this scheme is I'm not recopying anything, right? What's the downside of this scheme? Yes. The memory isn't locally allocated? Well, actually, I've allocated it. The problem is not that it's local or not. Okay? Yes? The access time is going to depend upon how many pointers I cruise through. Does everybody see that? To access this element will depend upon how many pointers do I move through. How many pointers will I move through to access the nth element? Log n. Does everybody see this? This gives me an array where, a souped up array, where in fact it's only going to take log n, it's going to take log n time to do each operation, okay? But I'm not going to have to recopy anything. Is this a good trade-off or a bad trade-off? Depends. You say it's a good trade-off? Well, let's think about that. The answer is probably it depends, okay? If I'm afraid of spending a lot of time copying, okay, then this might be a better thing. On the other hand, accessing an array in log n time doesn't seem like such a win. It seems like you've lost the beauty of what is an array, right? Now, why might this be better than a copying operation? Well, if I spent a lot of time on these copies, okay, you're saying, how much time does it take to do one of these copy operations? Okay, so when the time comes that I have stuffed my array of size n, and I now want to copy it, how much time does that copying operation take? Okay, moving back to my dynamic array, right? Let's go back to my dynamic array. How much time does it take to take an array here, which was of size n, and allocate an array of size 2n, and copy these elements over? How much time does that take? N. Does everybody see that? So this one write operation is going to be very expensive. Isn't that right? So why might this be a bad implementation? Let's say your computer is controlling a heart-lung machine. There's a patient at the end that's expecting every minute you're going to go tell it to breathe, right? If the computer got caught doing one of these long operations and didn't trigger the patient's thing going, that would be bad. Okay, or to be precise, one of these operations is very, very slow. Does everybody see that what's going to happen is, of these array operations, all but a log n of these insertions are going to take constant time under my scheme. Then 1 out of every, n over log n time, I'm going to have an expensive one where I have to do the copy. Does everybody get that idea? So his scheme, every access might take log n time. Under my scheme, certain accesses are going to take expensive time, right? But most of them won't. Any questions about that? Yes? Well, let's think what's going to happen. Why won't most of these things happen? Let's say we're going to do insertions, and we're going to figure out, every time we double the size since our last insertion, we do another copy operation. Otherwise, we're just going to stick it in the array, right, because we have room for it. Item number 1, we didn't have to do so. Item number 2 triggered a copying, right? Item 3 did not trigger a copying. Item number 4, is that going to trigger a copying? Okay, because we've doubled the size of the array, right? It was 2. If we double on every power of 2, right? When we do num 4, that's going to trigger a copying, right? Now we've got room for items 5, 6, 7, and 8 is going to trigger a copying, right? And now we've got room for 9, 10, 11, 12, 13, 14, 15, 16, right? Does everybody see that most of these operations are going to be extremely quick? But every time we double, meaning a total of log n times, in a total of n insertions, would we have copy things that are going to be delaying it? Any questions? Okay. Any questions about that? Okay, but one other thing I wanted to talk about before I get into too much detail here. How much total time will I spend, though, if I have a dynamic array and I fill it up with n things? I said that it will be big O of n times log n because I said there's n insertions, and each insertion might, each element of these insertions might be copied log n times. But in fact, actually, the total amount of copying done is less than you think. Okay? If we look at the elements from 1 to n, half of these elements were not touched n log n times, but these were all touched 1 time. Does everybody see that? And a quarter of the elements were touched 2 times. And an eighth of the elements, were touched 3 times. And a 16th of the elements were touched 4 times, right? Because if you think about how many times you were involved in a copying, it depends upon what element you were inserted, right? The first insertion got copied log n times, okay? In general, we have an analysis that goes something like this, okay? How many elements got copied 1 time? If I is 1, well, n over 2 to the 1. What is 2 to the 1? 2, right? So this says that n over 2 elements were copied once. For I equals 2, that would mean that n over 4 elements were copied twice, right? N over 3, or n over, which means 1/8 of the elements, were copied 3 times. Does everybody see that this analysis that I'm making about breaking it into runs, very few of the elements get copied many times? If we sum up the total amount of copying that goes on, we have the expression, the summation like this, okay? Which says that there's elements that are copied anywhere from 1 to log n times. And the number that are copied I times is n over 2 to the I. The total number of steps are, for each of these elements, is n over 2 to the I elements. Each of them is copied I times. The summation here, n is not a function of the variable I. We can pull that out. We get what is the sum as I goes from 1 to log n of I over 2 to the I. This is clearly going to be less than what we get if we summed it up to infinity instead. Okay? Because now we're summing up not just up to log n, but we're summing this up forever. Okay? Yes? Well, it will be copied because it's a question of how many times does the family have to move. When we add an element 1, if we have an element array of size 1, it will be fine until we do the second insertion. Now we allocated an element of size 2, element array. We had to copy it. This is fine until we do our third insertion. Then it's got to be copied again when we do our fifth insertion. Does everybody see this? Okay, and so it might be copied log n times. Bottom line, what is the sum as I goes from 1 to infinity of I over 2 to the I? You did that back in high school. I don't remember it exactly, actually. I do remember what the sum of 1 over 2 to the I is as I goes from 1 to infinity. What's the sum of 1/2 plus 1/4, plus 1/8, plus 1/3, plus 1/16, dot, dot, dot. What is that? 1, right? This is not quite that because there's that I on top, right? But if you think about it, 2 to the I is growing very, very fast. I is growing very, very slow. For a small value of I, this is still going to be bupkis, right? It's not going to get very big, okay? So, in fact, the sum here, it turns out, is always less than 2. And the result of this is that, in fact, the total amount of copying that goes on is only twice n. Not log n times n, but twice n. Okay? Any questions about that? Do people kind of see that, why that might be? Any questions? So this is an interesting example of something we won't do in here as much as maybe we should. But it's one where the simple analysis of what's the number of operations you're doing times the worst case yielded us an answer that was true but wasn't as tight an analysis as it really should be. Sometimes by doing more clever analysis, you can get a better bound than just maximum number of steps times the maximum cost per step. Usually that will do a good job. This is a proof that it doesn't always give us the tightest answer. Any questions? Bottom line, dynamic arrays are a good thing. They only cost us a total of, at most, twice as much work, okay, as a regular array would be, okay, without you having to allocate it in advance. Any questions? Okay, good. Now, linked structures, okay? Every one of you in here should have taken 214. You should know about links and linked lists. Linked structures are built out of pointers. Pointers are an address of something in memory, okay? It is telling us where to go to find something, okay? An address of somebody's mailing address tells the postman where to go to deliver your mail, right? Okay? And a pointer satisfies the same kind of thing. Now, when I think about pointers, I am an old C programmer, and so I think about pointers as a C-type pointers instead of Java pointers, which sometimes disturbs some of you. Okay, but they're really not that different in terms of their upshot here. What we're going to say is, just to help follow our notation, to get the address of a variable, we use AND that. To have a pointer star P gives us the item that we're actually pointing to. Okay, and there is a notion of a null pointer, which we can use to tell us when a pointer isn't a valid pointer, but represents the end of a list that we maintain. So how can we implement a linked list? Here is an example of a linked list structure. Each struct item in the list is going to be made up of something that is a data field, okay, and a linked field, okay, data field and linked field. The end of our list is a nil. There is a head of a list that we care about, okay, and we deal with that. Suppose we want to link Obama into this list of presidents. Okay, here we've got a pointer P pointing to a node Obama. What must we do to put Obama into the list of presidents? Okay, vote is a good thing, yes. But now what do we need to do as far as movements go? Okay, yeah. Traverse the list. Well, first of all, there's a question, where do I want to put it? Okay, is there any reason if I want to just keep a list of presidents? Can Obama go to the head of the list? Is it sorted or unsorted? If I look at this, Lincoln, Jefferson, Clinton, these are not sorted in this particular list, right? If I had to make it sorted, I would have to find the spot where I go and insert it. What are the mechanics you have to do to insert this guy into the list? Okay? Just to remind ourselves. Okay? We've got this extra pointer field here. We're going to make this point to the head of the list. And we're going to change this and have P the head of the list point over to here. Okay? If we do that, now we have a list that starts from here, goes to that, goes to this thing. Does everybody see that by changing 2 pointers you can insert somebody into the list? Okay? Any questions? None of the other items moved, which is why insertion into a list is a fast and clean thing. Any questions about that? So here, what can you do with lists? What are the basic operations? Well, one thing you can do is to search a list. Here I give you a routine that does a list search. Given a key field, a data item, you want to find where is Obama on the list. Given a pointer to the head of the list, how can I find whether or not Obama is there? Well, what do I know? If the list you're asking me search has nothing in it, then I know that Obama isn't there, because Obama's something. Okay? If the pointer to the head of the list, the item that it points to, is in fact what the key that you're looking for, return that pointer. If not, that means that you're at a list here. This is L. You would like to go to the next field of L. L.next points to the next item. Continue your search at L.next, and that's going to be the next item on the list. So this is a recursive program for searching in a list. Okay, given a list, see if the head matches. If the head does not match, search in the tail, which is L.next. Any questions about that? How much time will this procedure take to search through a list of n elements? Okay, yes. Worst case will be n. Why is that? Okay, because I'm doing something that takes constant time, something that takes constant time, and then I'm resuming my job in a list that has one less element, right? So after a constant amount of time, I have made progress of one element. Okay? If I do this n times, I will have spent n times the constant steps, or order n time total. Any questions? What other operations? Well, there is basically, just actually did this, there is an insertion operation. Okay? And I encourage you to, work through and figure out this thing. How would I insert an item into a list? I just did this actually. But basically the key idea here is I have an item that I want to insert. Okay? I create a node where I fill my data item here. I have an extra pointer that has to be dealt with. Either I could insert it at the end of my list where I had a nil pointer. Okay, and if I have a pointer to this item, I can change that pointer to simply go point there. Or like I did before, if I have a list that is pointed to starting at L, okay, I can change L by having L point to my new node, and the end of this thing point to the rest. Okay? And if so, this element's been spliced at the beginning. Any questions about that? Okay? I will assume in 214 you have gotten somewhat comfortable with pointer manipulation. Any question? If not, go through these carefully, okay, to make sure you understand how you deal with pointers. Any questions? What is involved in the remaining main operation, which is to delete something from a list? And again, there are a bunch of different ways of doing this in terms of actual code mechanics. But why is this a tricky thing? Okay? Here I have a list that is pointing. Let's say I'm drawing my list. This is nil. I have my element L that is pointing here. Suppose I want to delete an element from my list. If I am given here, first thing I've got to do is find a pointer. If this is the element X, I delete the element with Skeena in it. First thing I have to do is to find what node contains the item that I want to delete. Does everybody agree with that? Once I have this element, what do I have to do to delete it? Okay? Note that for this element to be deleted, it's not enough to have the element. I have to know who is the guy before me on the list. The way that you delete me from this is that you splice me out. You run that pointer around me. Does everybody see that? And so what I really need is to find the predecessor pointer, the guy before me. Okay? And if so, then you just have the guy, to delete me, you copy the value over the value of what the predecessor that pointed to me. Instead, have it point to the guy that I point to by copying over that variable. The critical item is probably this one. Okay? Any questions about that? Okay? Actually, no, that's not. The critical item that I just talked about is this one. My item P, okay, last dot next is going to be what P dot next is. Any questions? And then there are boundary conditions to consider what happens if I delete the last element, okay, and possible boundary conditions. What if I delete the first element? Now my predecessor is the original variable here, okay, rather than an element, a node in the list. Any questions about that? Okay? So deletion from a linked list should take how much time to find the element? Potentially n. Once I have the right pointers I need, how much pointer manipulation is necessary to delete the element? Okay, once I have the pointer to the guy before me, it should be constant. I'm just doing one or two variable changes, copying a value of a pointer around. Any questions? If you are not comfortable with pointers, this is an excellent time to either take 214, which is the prerequisite, or go and review this. Any questions? Okay, if you've already had 214. Okay, good. So what are good things about linked lists? Let's think about linked lists. Why are linked lists good things? Okay? Yes? You say they don't use more memory than required. Now, this is one you have to be a little bit careful about what you're actually saying. Do linked lists use more memory than required? How much memory does, in terms of, let's say memory quanta, how much memory does a linked list on n elements take? 2 times n, because you need to store the pointer and the data field and the pointer, right? So on one level, it does take twice as much memory as before, right? Okay? Yes? Okay, so what you're saying is if I was doing my dynamic array thing that I was just telling you, right? I might waste half my space because I allocated twice as much. And I guess you're right there, okay? But there is a difference. Pointers, first of all, do take space. That's one thing to recognize, okay? And if I knew the number of items I had in advance, okay, an array in principle would be more efficient than the linked list. What is really true is that linked lists give you flexibility, okay? There are certain things that make linked lists more flexible. First, okay, I can have a memory where you can imagine a world where I cannot have n units of contiguous memory left that hasn't been allocated. But there are more than 2n spots of memory in disconnected smaller pieces. If so, I could build a linked list on n items the way I couldn't build an array on n items. Okay? So linked lists, I won't complain about an overfill thing unless the memory is actually full. That is one good thing about a linked list. Okay? It uses bits and pieces of memory that, let's say, you might not otherwise be dealing with. In certain ways, insertion and deletion can be simpler in linked lists than in arrays, or more efficient. If, let's say, I wanted to maintain a sorted array of items, I have an array of items here. Okay? If I delete this item in the middle, what do I have to do to maintain a sorted array? I've got to shift all of this stuff over by 1, right? How much time might that take for an n-element array? N, okay? If I have a sorted linked list, in principle, and I have the right pointers I need, how much time does it take to delete that one element? Constant. Does everybody see that there's a trade-off here? Right? Okay? So what's interesting is dynamic memories, linked listings give me more flexibility. And in particular, they give me more flexibility on how I use my memory than a array does. Okay? And sometimes linked lists are good things, and sometimes arrays are good things, and we need to understand why for both of them. Any questions? Okay, so what else do we need to know about data structures? Okay, I'm going to try to go through this fast because I don't have too much time. But one data structure that you guys learned about were stacks and queues. What were stacks and queues? They were data structures where you stored things that were independent of what you were looking for, but were ordered by position of insertion. Does everybody get that idea? What was a stack? Where did you put a stack? That was last in, first out, right? What was a queue? First in, first out. Okay? Which is a better thing for a data structure, a stack or a queue? It depends. Okay? It depends what you want to model. If you wanted to have a data structure for maintaining a line at a bank, which is a better data structure, a stack or a queue? A queue. Why is that? It's because the oldest guy in line gets pissed off if the guy who came in later gets treating them, right? A queue seems fairer. Which more accurately models my refrigerator, the way I deal with food, okay? You know, when I buy new food, where do I put it? At the front of my refrigerator. When I am hungry, what do I reach for? The front of the refrigerator. First in, first out, right? First in, last out is what happens with my refrigerator, and is what happens with a stack. Any questions about that? Okay? Now, for a lot of items, it doesn't matter whether you're treating them fairly. If they're integers, do they get tired of waiting in a queue? Okay, or a stack? The answer is no. Sometimes it doesn't matter. Okay. Give me one more minute here. I do want to talk about this because this is going to be critical for the problem of the day, which is next week, and is a critical problem of the day. The mother of all data structures that we're going to analyze in an algorithms class or use in an algorithms class is a data structures for an abstract type called a dictionary. A dictionary is an abstract data structure that does 6 different operations. Okay? And let's define these operations very carefully because we're going to use them, study them next time. Actually, for the daily problem, you're going to need to know this. So, in a search, we are given a data structure and a key item. Okay? And you're asked, does there exist a value with that key item in the array, in the data structure? Okay? In an insert, we are given a data structure and a pointer to a record, okay, which contains that element, that key, and any other data, right? When you insert Skeena into the database, the key thing is Skeena's name. Maybe with Skeena's database, you're going to want to know his address, his height, his weight, stuff like that. The full record that you're inserting, okay, of the key and the other fields, that's pointed to by X. Delete means you are given an item, an array, or a data structure, and you are given an X and not a K. You are given a pointer to the item in the data structure and told to remove it. This is going to be important. Notice here, when I'm searching, I am using a key. When I am deleting something, I'm assuming you already have found the thing you're deleting. So you don't have to pay the search cost again. Okay? Any questions about that? Do people see that? What if you don't have a pointer to the item to delete? How do you get a pointer to the item to delete? Search, okay? So the cost of doing it in that case is the cost of search plus the cost of delete, right? But if you have the pointer, you can get it done cheaper possibly. What are the other operations? We are given a min and max operation. In any one of our dictionaries, we will assume there is a total order on our keys. Okay? In alphabetical order, it goes from A, Acme to ZZZ top, right? There's a min and a max is what is the largest, first and last in alphabetical or numerical order. And finally, last thing, and then I will let you go. Next and previous, okay, are operations that work on the total order. Okay? They are giving us not the, that if I give you the smallest element, you return the second smallest element. Not in where they sit in key space, not in physical space. Okay? Do you see what predecessor and successor mean? They are in logical space. Read in the book before you do the next problem of the day, and we'll talk about it then. Thanks for your attention. Talk to you then.